It's already like sometime in the future. If to do some like full like range level things.
Okay, I think we're gonna get started, and okay for people to trickle in just to fire Daniel like a few more minutes to squeeze in the hour. So I to say, I'm really excited about the work Daniel has done, and actually very grateful for all the time I spent with him. It was like every meeting there's something new. He's super creative, and actually I think one of the unique people in connecting really device behavior and physics, being able to do device design, connect that to circuits and systems, and really kind of think from kind of molecule level to kind of the system level. So I really appreciate that. You learn something every day. I think it's also a super challenging project and our group's introduction to quantum photonics. So really appreciate that learning. Also, doing all that while at the same time being a great mentor to a whole bunch of people. This is like, I would say once in every few generations, you get a student like that who's willing to donate the time and really bring people up to speed, undergrads, high schoolers, grads, so that's like one of the treats that I'm really happy to see Daniel, and hopefully he'll develop this in the future or nurture it even more. Okay, so without further ado, let you hear Daniel's talk.
Okay, yeah, thanks for the introduction. So my name is Daniel Kremnick. I'm a PhD student in Vladimir's group, and I'll be talking about the work I did over approximately the last 6.5 years as a PhD student here at BWRC. So I'm going to start with an outline of the talk, which is going to be in 4 parts. So the first part is kind of motivating why we're doing this work on putting quantum photonics into CMOS. And that's related to scaling challenges in silicon photonic quantum computers. And the second part is going to be talking about a heralded single photon source with integrated control electronics that we built. The third part is going to be related to on-chip control of integrated optical filters with greater than 100 dB of pump projection on the same chip. And then part 4 is like a little bonus, which is going to be about enabling optical circuit switching in AI data centers with fast tuning channel drop filters. Okay, so why are we interested in silicon photonics for quantum in the first place? Quantum photonic computing is one way of building quantum computers, which we think can solve problems that are impossible with classical computers, even AI. So that's why everyone's interested in that. And if you try and build a quantum computer with optics on an optical table, it starts looking something like this. It's not very scalable. So silicon photonics kind of promises to take all that and miniaturize it into microchips that are fabricated in a CMOS foundry, which is like the way we know as humans of building the most scalable and large-scale systems in the world. And that's applicable both to quantum communication systems, so how you connect quantum computers together, and the computing elements themselves, like the actual qubits and detection and all that other stuff. So we kind of believe that all of the elements, state preparation, state manipulation, and state readout, can be miniaturized from bulk optics or fiber optics into nanoscale waveguides that are patterned on a CMOS chip. And that allows us to build all of the components needed for a quantum computer, including heralded single photon sources. Those are like the qubits, which are encoded depending on which waveguide they're in, potentially, optical transformations, and measurements with single photon detectors that allow you to build the gates and all the other components that you need for quantum computing. There's a lot of different proposed mechanisms for being able to implement the actual computing, from KLM to like measurement-based, and I won't get into that. But basically, people kind of think that all the elements are there to be able to do these things in a CMOS platform. So let me start with like a brief overview of the field. So kind of in the 2000s, people figured out that silicon, which is the material of CMOS, can generate heralded single photons or quantum correlated photon pairs. And they sort of demoed that can be done in a silicon photonics chip. And then in the 2010s, people started scaling this up and building maybe tens of quantum photonic devices per chip. And now in the 2020s, people are regularly building like hundreds of quantum photonic devices per chip and starting to do bigger systems with, like several qubits, or trying to get to the scale of maybe dozens of qubits or something like that on a chip. The problem, though, is that when you look at how people expect to control all of these optical devices on a CMOS chip, you see this nice, big optical system with a lot of devices. And then in the papers, people show that there's like, this little black box on the side, which is like very small and probably easy to do, which is the control electronics. And so, the photonics take up a lot of space because the wavelength of light is pretty long. The wavelength of electrons is pretty small, so probably all of this takes up very little space. And so obviously, it's just this little simple black box on the side. The reality is that when you start scaling up the photonics, actually you end up with like a pretty big bottleneck on the control and the I/O for all of the electronics. And so what ends up happening is when you reach this scale of like hundreds of devices per chip where people are, you start to run into severe bottlenecks in being able to control all of them. And then you have, so bulky external equipment and cables and stuff like that. So you're sacrificing a lot of benefits of a CMOS platform if you don't find a way of co-integrating the electronics nicely somehow. So silicon photonic integration has delivered a lot more photonic devices per chip, but we're missing a key element, which is the scalable feedback control. And that's what's addressed in this work by directly integrating large-scale CMOS circuits and quantum photonic devices onto the same chip. And in particular, I'm going to focus basically all of the quantum stuff in this talk on state preparation. So building good heralded single photon sources. But then, we can take the same electronics, same photonic devices, and then kind of build the rest of the system in the future as well. Okay, so let's talk a little bit more about silicon photonics. So CMOS manufacturing basically uses lithography and silicon wafers in order to build things as like a sandwich of silicon and metals that allows us to integrate nanoscale transistors with metal interconnects and then eventually break them to the outside world, which is how we end up with CPUs and billions of transistors all on a microchip inside everyone's phone. So silicon photonics is basically taking the same technology and using it to fabricate optical devices. Silicon happens to be transparent at telecommunications wavelengths of, let's say, like 1300 nanometers and 1500 nanometers. So it actually makes a really good high index contrast waveguide. And what that allows you to do is shrink fiber optics down to the size of tens or hundreds of nanometers and put them onto a silicon chip. So what we're doing is kind of a step beyond that. We're not just using two separate types of similar process nodes in order to build up the photonics and electronics separately. We're proposing and implementing them on the same chip. So we use a standard 45 nanometer SOI CMOS process with 0 modifications. And we basically just etch part of it in order to reveal optical devices that have been patterned in the silicon layer for transistors. And that basically allows us to create a very high density of interconnects between electronics and photonics with greatly simplified packaging. It's immediately scalable to volume production. But there are some challenges with the optical device performance, and we'll get into that later. What's really nice is that in 2022, GlobalFoundries debuted a co-optimized process called 45 SPCLO, which is based on 45 RFSOI, which is where the first half of this work takes place. And that actually makes the performance of the photonics much better. Okay, so part two, first part of actual content. So now I'm going to talk about heralded single photon sources with integrated control electronics. Okay, so let's say I've got a silicon waveguide. That's the material that we have in CMOS for guiding light. How does it generate heralded single photons? So the answer is that basically every type of material that light travels through generates some kind of polarization response. And if you have any anharmonicity in the sort of atom-to-atom bonds inside of the molecule, inside of the material, then you end up with a nonlinear polarization response. So instead of the polarization of the material being directly proportional to the electric field of the light, you get these higher order terms. That's called nonlinear optics. So in silicon, we don't have a chi2 term, a second order term. That's kind of like second order harmonic distortion. We have a chi3 term. And basically what happens is if you take a laser, which is like cosine omega t, and you shine it into the material, you now get cosine cubed omega t and all kinds of nonlinear effects like new frequencies of light being generated. So the specific process that generates quantum correlated photon pairs is called spontaneous four-wave mixing. in which two pump photons, which are the green photons on the left, get annihilated, and they create a pair of quantum correlated photons called the signal and idler that are at a different set of wavelengths. For all the RF people who are familiar with intermodulation distortion, this is kind of like a quantum mechanical version of intermodulation distortion, where some tone is intermodulating with vacuum noise that's happening at all frequencies, and it's just spontaneously producing new frequencies all over the place. And so it turns out, if you take a silicon waveguide or a Chi3 material, you hit it with some kind of pump laser, you're going to get, a lot of residual pump photons out, but every once in a while at offset wavelengths with energy conservation, you're going to get time energy entangled photon pairs. And if you put those into single photon detectors, you're going to get a nice coincidence histogram where you can resolve those from all the background noise and then use one of those to herald the other one. So when one of your detectors clicks, that tells you got a single photon in the other channel. And that's how you build a heralded single photon source in silicon photonics. Okay, let's investigate that a little bit further. So people started with straight waveguides as their heralded single photon sources. But it turns out you need a very long waveguide to do that. When you wrap that up, it turns out, one heralded single photon source is like 1 millimeter by 1 millimeter. It's not super scalable. And then energy conservation happens at a very broad range of frequencies. So you get photons all over the place in terms of frequencies. And you have to do a lot of post filtering in order to select particular bandwidth time modes that can actually undergo quantum interference from one source to the other source. So this is good for a demo, but it's not really good for a scalable system. The way you build a scalable system is with a microring resonator. So you take an optical waveguide and you bend it into a circle so that when an integer number of wavelengths lines up inside the waveguide, you have a resonance. And that resonance strongly enhances the spontaneous four-wave mixing efficiency, and it concentrates it at particular wavelengths, which makes it really easy to get quantum interference between different microring sources. And they're like tens of microns in diameter, so it's a very scalable approach, at least in comparison to the spiral waveguides. But there are some challenges with controlling microrings. The first one is that you have to calibrate them across process variations. They don't all come out exactly the same. The second is that they're very sensitive to temperature, and they can even have temperature bistability, where depending on how you initialize their temperature and tune them around, they'll do different things. And there's only one particular way that you can get them to be exactly on resonance. A third challenge is that you've got all this residual pump light bouncing around your chip, and you want to separate your photons from that. So that requires very high extinction filtering. And so as a result of all these challenges, when people are building larger and larger quantum photonic systems, they're still relying on spiral waveguide sources, which have pretty poor performance. So we want to enable people to use microrings. All right, so a little bit more on the details of how you see these variations in microrings affect you. So you need all the sources on the chip to be locked to a common wavelength and to produce a common set of output wavelengths of light. But when you get the microrings from the factory, there's a spread in the resonances. So we have to align that. And that's done by thermal tuning. We can build a heater into each microring and then get all their temperatures aligned. Not all their temperatures aligned, but all their resonances aligned by tuning the temperature. And the second is that there's a snapback effect where as you put more and more light into the microring, the light actually keeps it up. And so there's some hysteresis there, and you have to initialize them properly. So that basically makes it very difficult to coordinate a large scale system built out of these microrings. So here's a picture of what we built, which is a single chip that contains microring cavities, high extinction pump filters, and all the control electronics that you need in order to control all of them locally on the same chip, and tune them so that they lock to the pump laser and maintain their performance over time, even as there's thermal crosstalk. And it actually works so well that we don't need any sort of external tech or temperature regulation, although we would certainly benefit from it. But our demos are without a tech, just to show that, like, hey, everyone else needs really careful thermal regulation and a graduate student turning like 20 control knobs to keep this thing going. And we just have circuits doing it automatically. All right, so let me talk first about the microring resonator that we built in order to allow the control electronics to basically sense what's going on inside of it and then tune it. So we take a standard microring and we basically put P and N doped spokes inside of it to extract small amounts of photocurrent that are generated by defect and surface state absorption. Since silicon is mostly transparent, but every once in a while, some light gets absorbed. There's also 2-photon absorption at higher powers. And specifically what we did that's like kind of an advancement over the state of the art, and two guys in Milos's group, Imbert and Georgi, really spearheaded this, is basically taking a look at the strength of the nonlinear interaction and the dispersion of the resonances and optimizing the parameters of the waveguide in the microring so that we have the highest pair generation rate efficiency. So we're not just picking, a random value that looks about right for the radius and the width of the waveguide, all this other stuff. It's all very carefully traded off in order to optimize the strength of 4-wave mixing. And I think we're the first to document exactly how that's done. So the key things that you have to do on the design side are basically keep the dopings and the spokes away from the actual propagating light inside of the waveguide. But you don't want your ring to be too large when you do that, because higher mode volume is a weaker nonlinear interaction. So there's like a lot of balance you play in order to optimize the Q factor without making the mode volume too high. And so here's what this device actually looks like on our first chip. So you can see a silicon waveguide that is coupled to the microring. The silicon waveguide in this photo is 400 nanometers wide, to give you a sense of scale. And the ring's got 20 microns in radius. Okay, and then here's the circuits that are attached to the microring in order to implement the feedback control. We basically take the photocurrent, sense it with some transimpedance amplifiers, put it into an on-chip A to D converter, do some digital averaging in order to try and reduce the noise. And then we've got a delta sigma DAC that's driving a heater that's in the middle of the microring and can adjust its temperature in order to try and lock it to a pump laser. And there's both an on-chip controller and a scan chain interface so that we can use an FPGA to program these things. We mostly just scanned things out and did things in Python because I was very flexible, but it's slow. So in the future, we're going to move to hardening all of that onto the chip. Okay, and here's the transmission spectrum in subfigure A on the top of the microring, just to give you a sense of like what you're looking at when you plug this chip in and you start shooting a laser at it. So we've got some unaligned filters for now that are giving you little dips all over the place. So ignore those. The blue, green, and red lines are from that microring that I just showed you. And they're very high Q resonances on the order of 100,000. Although, we've improved that subsequently. So we basically have one wavelength in the center that we're picking out from these periodic wavelengths that extend, in both directions. We're hitting that with a pump laser, and then the blue and red wavelengths, the signal and idler, are where the output photons are coming out. We have about 0.62 nanometers of tuning range with the heater design that was on that chip, which is kind of low, but it actually means that you get a very, very precise step. So you can very precisely tune this high Q resonator. And then, as you can see on the bottom right, if we take the laser wavelength and we scan it back and forth with like kind of a moderate amount of pump power here, you can see that bistable behavior that I was describing before. There's only one relative way of moving the laser and the microring resonance that actually gets you a lock. And that self-heating bistability is greatly enhanced by the high Q factor of the microring. So this is like happening at much lower powers than you would see it, for example, in like a low Q modulator ring that's being used for datacom or something like that. That's why we're seeing this bistability even at like -10 dBm. Okay, so here's the first demonstration that we did with this system. We basically took a fixed pump laser, cleaned it up off chip, so get rid of all the ASE noise because that can contaminate the signal and idler bands. Sent that into the chip, locked the microring to it with the on-chip circuits, and then sent the output to a set of off-chip filters with something like 160 dB of extinction of the pump wavelength, and exactly the right pass bands to pick off the signal and idler photons, and those are detected in SNSPD. So, in order to lock the microring to the right wavelength, what we did is basically start it off hot. So you initialize your heater at its max code. You scan it down and take a look at the photocurrents. You figure out what the peak is. You say, I'm going to lock to like 95% of the peak, kind of balancing on the razor's edge of that thermal bistability hysteresis. Then you reinitialize it, scan it back, and turn on a feedback control loop that keeps it stable there. And the initial scan is necessary because the microring's responsivity and all of the gains of the TIAs, all this other stuff is sensitive to process variations. So you don't know a priori, like what is going to be the photocurrent code for this particular microring that's the max. So you have to do the calibration. And then you can see that as we're sweeping it, the green plot shows the transmission. So we're kind of getting into the dip, then snapping off of the dip, and then reacquiring the dip and staying locked there. And now the last two plots are pretty exciting. Those are basically showing that coincidence peak that I showed you in the earlier slide with the single photon detectors, that's being resolved from all the background noise, and we're getting quantum correlated photon pairs being generated here. And they have it in this experiment, a decent coincidence to accidentals ratio of 50, but depending on the pump power, you can kind of change that. And I'll talk about the noise mechanisms later that are limiting that. So the second experiment that we did is a little bit more aggressive. So since we have all of these source rings on the same chip and filters and stuff, we decided to like really investigate and prove the robustness of the system by taking the nearby source ring and just pulsing it aggressively, like all the way on, all the way off, to create a thermal disturbance on the same chip. And that's shown in orange. So in red, we're basically doing this calibration scheme, if you're looking at the first plot. Then we're locking the first microring. And then we come in with a second microring and we pulse it. And so when the feedback is turned on, you can see that there's a little bit of disturbance response. So if we improve the bandwidth of the loop by moving the code from Python onto the FPGA and eventually onto the chip, those will go away. For now, we have a very slight disturbance in the ADC code and a barely perceptible disturbance in the pair rate and CAR. CAR is the quantum signal to noise ratio, how much coincidences there are in that peak versus the background noise. And the second part of the experiment, we turn the feedback off and we repeat the same pulse. And you can see the microring immediately snaps away from the laser and kind of stops generating pairs. So there's a critical function when you're scaling up these systems and controlling more and more devices on the same chip that the feedback circuits provide.
Quick question.
Yeah.
How close can you get to the 95% to the peak?
Yeah.
How close can you get? And does that impact efficiency?
It barely impacts efficiency because the amount of misalignment that we have is a very small fraction of the line width. I don't know the exact number, but this is pretty close to where we can get it. But I mean, that's limited by like fiber stability, right? Like at a certain point, because we're just manually aligning the fibers, you'll just snap off randomly because they're changing. In the next generation chip, we have a pump monitor that monitors that misalignment. And so we can try and correct for it. But 95 is about as close as we can get right now. And it's really just limited by the stability of the system. There's no kind of fundamental there. Okay, so here is a larger set of data points that shows the pair generation rate and the properties of the single photon as a function of the amount of power we're putting into the chip. So in a real system, you may want to trade off some of the properties of the source in order to either get more pairs or better signal to noise ratio. So you'll dial in the exact power. And we're just showing here that over about an order of magnitude of power on the chip, we have the dynamic range to keep this thing locked and generating pairs. So in the left plot, the blue data points are our directly measured count rates on the SNSPDs after a bunch of loss mechanisms and their non-ideal detection efficiencies. And then the red data points are us very carefully calibrating all the parts of the system and then de-embedding those losses. And what's really exciting about the plot on the left, which we did in the past year, so pretty late in this project actually, but I think it was worth it, is that if we take the measured spectra that I showed in the previous plot, we fit all the curves with the Q factors of all the resonances. We use the simulations of the nonlinear coefficient in the microring. Then we get the green curve, which is the predicted pair generation efficiency. And it matches very, very nicely with the actual data that we have for that particular microring. The design point is the orange curve, which is slightly higher. And I actually characterized variability across, I think, like 6 or 7 different fully packaged chips. And you can see that as you average over the variability in the source ring, you get closer and closer to this design point. So that kind of verifies our whole design procedure. And it really allows us to extrapolate into the future. Okay, with improved microrings, where can we get this? So we kind of have that perfect trifecta of theories, simulations, and measurements that are all agreeing, which you want in experimental physics before you kind of feel like you really understand what's going on. And then the curve on the right is showing the coincidences to accidentals ratio, which is like the quantum signal to noise, and the G2, which is a measure of like how much like a single photon, heralded single photon is this. The G2 is measured by taking a beam splitter and putting it into one of the channels. And what that allows you to do is basically say, hey, if I really only have one photon in each arm, then when this detector clicks, I better only get a click on this channel or that channel, because the photon had to make a choice at the beam splitter. If I have any correlation between these two channels, that's something else. That's not a single photon state. That's like a multi-photon state or noise or something else. And so having a very low G2 like this really proves that we have single photon emission. Thanks to the reviewers of our paper for making us do that. Okay. All right. And so here's a larger scale demonstration that we did with all of the photon pair sources on this chip active. So we got a dozen of them, and we're basically locking one of them, and then we're playing back the same locking waveform on all the remaining sources on the chip to kind of simulate what it would look like to lock all 12 sources at the same time. We can't actually align fibers to all 12 sources at the same time just because of how our grading couplers are arranged, but we can emulate the same waveform. And so this basically shows that over the course of an hour, we can keep this whole system stable. And it's like a very large scale demonstration. I'm not aware of anyone doing something like that, even using off-chip circuits. Maybe PsiQuantum, but they're never going to publish it, only until the whole system works. One other comment that I'll make is that, again, we're kind of limited by all of these control loops being prototyped in Python, which is why you see the calibration taking like a minute or something like that. If we take the code that's running in Python and put it on the FPGA, all this shrinks down by a factor of a few thousand, and then on the chip it can be very, very fast. And so that kind of addresses a concern that you might have had from looking at the size of the circuits, which is, okay, so you miniaturize the source to make it small, but then you needed big circuits next to it, right? So the circuits are now way bigger than the photon pair source. But it turns out that the circuits are operating at like 60 megasamples per second, and we're only using them at like a few hertz in order to be able to do this thermal locking and compensation. And so that means that you can actually multiplex the same ADC and TIA over many photon pair sources. And so I just ran the numbers of like, what is the circuit area overhead as you scale this up? And it could still be further optimized, but it kind of goes favorably. Like your future systems, as you control lots of microrings, are going to be dominated by the size of the photonics, not by the size of the electronics. And that's kind of what you want. And then we have a full paper about this part of the work on arXiv now, so you can go check that out. It was just published a few weeks ago. Okay, now I'm going to move on to part 3, which is the on-chip control of optical filters with 100 dB or more of pump rejection. Okay, so why do we need pump rejection filters? The first reason is that when you hit the microring with a pump laser, it doesn't have perfect extinction. You could attempt to critically couple it and try and get very good extinction, but actually to optimize the pair generation efficiency or the heralding efficiency, you want to be overcoupled. And so you end up with some light still getting through the microring in the bus waveguide. And the second reason is that, well, when you shine light into a chip, not all of it actually gets into the grading coupler. Even if you have a very efficient grading coupler with like a dB of loss, you still have some amount of light that's kind of going into the substrate. And that light can scatter in like a light pipe inside of your chip all the way to the output grading, entirely bypassing your on-chip filters or photonics or anything else. So it kind of can contaminate everything. So those are factors that have previously basically prevented people from integrating everything onto one chip. Like sometimes people have 2 chips where the filter is split between 2 chips and then they have a fiber going between them. But that's not very scalable because the fiber pitch you can package with is pretty big, and you take a lot of losses when you do that. So you want to really build everything on one chip for your source. So here's a calculation just using the parameters of that source I showed you before to figure out like about how much pump rejection you need. So the green, blue, and red curves are with different on-chip pump powers, showing the coincidence to accidentals ratio, which is quantum signal to noise, as a function of how much pump rejection you have, measured from the input fiber to the output fiber. And you can basically see that you end up with some limit on the right side that's due to multi-pair emission, just from the statistics of the spontaneous photon pair source. And then there's some limit on the left side that's related to pump leakage. So unless you have like 100 dB or more of pump rejection, then you're going to be dominated by pump leakage rather than sort of the fundamental properties of the pair source, which is what you want to be dominated by. I'll also note that at low CAR, we have pretty good agreement of this particular model, which just accounts for multi-pairs and residual pump versus the source we measured. Whereas at low powers, the predicted CAR is much higher. And that's because we're not accounting for spontaneous Raman scattering, which is a separate noise mechanism that occurs in the cladding material of the waveguide and sort of contaminates everything with a low amount of noise. So I'll talk a little bit later about how we plan on mitigating that in the future. But basically the takeaway from the slide is you want 100 dB, at least 120 dB to be like really certain that you're not contaminating things. Yeah.
Good question. So is there a way to drag the corner to the left? Because 100 dB is kind of definitely a
Yeah, you can make the pair generation efficiency higher. And when you basically have more efficiency of generating pairs, the background noise matters less. And we have a way of improving that by like 1,000. So the pump rejection requirements will be reduced in the future. But it's possible to build filters like this. So that's what we've done. Okay, so what's a compact way of building a filter that has very high extinction? It turns out that by taking microrings and cascading them in series, you can basically get extremely high rejection. And what's nice about this topology of filter is that in addition to being compact, because it's using resonant devices, unlike other types of filters in integrated photonics, we have a basically guaranteed amount of pump rejection from one waveguide to the other, because the rejection is coming from the off resonance response of the filter. So when these rings are not non-resonant, what's basically happening is that your rejection is coming from going from one coupler to the next coupler to the next coupler to the next coupler in a single pass. And each of those couplings is like 0.1 or lower in terms of power coupling. And so you just put more of them in series, and off resonance, you have to go through lots of passes, right? So we got 6 rings here. So, like a dozen couplers or so. And that quickly cascades exponentially. So we can have very high degrees of pump rejection while maintaining a low passband insertion loss, because the passband response comes from the on-resonance response to the rings. So unlike other types of filters where you have to align the stop band response, which is pretty hard to do, like very high rejection across a narrow range of frequencies, here we kind of get the high rejection automatically, and we just have to align the passband for low insertion loss. A challenge is that you don't have zero passband insertion loss, as is shown in these ideal calculations. You take some passband insertion loss from the intrinsic Q of the microrings, and basically that prevents you from cascading like arbitrarily high numbers of microrings, because you'll start adding passband insertion loss as you do that. And there's kind of an intrinsic Q factor limit that is like a contour of achievable stop band attenuation versus the passband insertion loss that you're forced to take. And so it turns out for our system, somewhere between 4 and 6 microrings is about optimal. It gives you enough insertion loss and decent, very much sub dB passband insertion loss. One other thing that you don't want to do in order to get lower passband insertion loss is couple the rings very strongly and have a very, very high bandwidth for your passband, because that's going to emit more Raman noise. So there's kind of an optimization that you have to do here. Okay, so here's like a Gen 0 system that was actually taped out before I started my PhD, but never tested by Kale from Milish's group. And so we packaged it and tested it as kind of a proof of concept and bringing up all of our measurement capabilities. It has a source ring with a thermal tuner, no feedback, and then a cascade of 4 second order filters with thermal tuners. And having a cascade of second order filters is like lower performance in terms of insertion loss, but it's way easier to align. So that's why it was done this way. And we have a conference paper from a few years ago where we basically showed that we can align the source ring with the heater inside of it, and then tune up these filters so that we have decent passbands, maybe like 4 or 5 dB insertion loss. So not great, but like a good proof of concept. And we're able to get some amount of coincidences and quantum signal to noise out of this. Yeah.
So where is the challenge with alignment if you have integrated photocurrent sensing in rings?
I'll get to that later. So it's not trivial because as you couple the rings together, it's not just you keep maximizing the photocurrents. There's like a very complicated way in which the rings, couple power between each other. And so you might actually maximize the photocurrent, then couple them better, and then the photocurrent goes down. So it's not trivial to do that. And initially, we didn't have built-in photocurrent sensors. So it was all being done from the drop ports. OK, so one comment I'll have here is this is very early in our setup. We had like 10 dB of grading insertion loss, and we were really bringing up the system at the location where we were doing the SNSPD measurements. So the performance here is quite poor, but it at least is a proof of concept of all of this stuff being contained on a single chip. And here's a characterization of the filters that we actually integrated with the system, where we have feedback control around the source ring. So the ultimate goal of this system is basically bringing the ASE filter on chip. So there's a second order filter for that, bringing the source ring and feedback control on chip, and then bringing the pump rejection filtering off on chip so that you basically just plug fibers into this and get time energy entangled or time entangled photons out, depending on how you pump it. The chip we taped out has 4th and 6th order filters, and I'll just show the characterization of the 6th order filters. We just focus on those because they're going to have more pump rejection. So we basically, we haven't gotten to the point where the system is hooked up exactly as shown yet. We're just looking at one filter, and we put a photodetector on the drop port in order to try and align it. One trick that we did is initially when your filter is totally misaligned, you don't really have transmission, so you don't see a signal and you can't align it. So what we did is we used an EDFA that's unpumped, so just making broadband ASC noise, and we put that into the input of the filter. And regardless of where you have some small amount of alignment between the initially misaligned rings, you get a little bit of transmission. Then you run an optimizer on that. Then you switch over to a fixed laser where you want the filter to align. You run another optimizer, and then you're like kind of close to alignment. But it turns out that in order to get this like order of 1 dB insertion loss as the filter is designed, you still have to tune things manually. Like this system does not in practice operate autonomously. I know there are papers where people have published that you just run an optimizer on a high order filter and it works, but like if you do that experiment in real life, maybe it works like 50% or 60% of the time or something. It's like I wouldn't put that into a product. We also have somewhat limited tuning range here. It's maybe like 4 nanometers or so, and so that limited tuning range actually prevented us from aligning the filters and the source ring in this first system, just because they were initially too misaligned, and like the 0.62 nanometers and the 4 nanometers of these filters didn't cover enough range. But that's just a heater design issue that we can fix in the future. And yeah.
So would there be possibly a systematic way of scaling up the initialization or more efficient initialization routine? Because if you
yes,
use
that's what I'll get into.
Nice.
That's one of the things that we worked out in the next generation. So like black box optimization is not super robust, and like if it doesn't work, you don't get a really great readout of why it didn't work and like where your system ended up. So we have a better way. But what's exciting about this chip is we actually did measure over 100 dB of extinction on the chip. So I aligned the filter with the optimizer. Here, the passband is not perfectly aligned because I didn't do the final manual tweaking step, but this is just with the EDFA and then laser and 2 passes of optimization. And then what I had to do is, if you just look at the blue curve, which is the continuous laser sweep, you see something like 90, 95 dB of extinction. And that's because the laser has ASC noise, like noise around its sides. And if you have an aligned filter, the noise goes through the aligned filter and contaminates your your measurement of the stop band. And so what I did is added a tunable ASC filter that steps with the laser, not continuously though, just because the hardware couldn't be synced that way. And so when I enable that, you get the red points, and you can see that we're basically below the noise floor of the photodetector and seeing 100 dB of extinction. An even better way of doing this experiment is with single photon detectors, but that's a lot more technically involved to do. So this is the way I was able to do it for now. And we had to buy like a really nice in-gas cooled detector in order to do that measurement as well. But thanks for sponsoring it. Like a year ago we bought it, and I was like, I'm gonna stay and do this measurement. And here it is, and it's in the paper. Okay, so the next step after this system was basically transitioning to 45 SPCLO, that process that I mentioned before, because that came online around the time that this chip was being tested, and we were thinking about the next generation. And so what's nice about CLO is that you don't have to do this etching step. So it's like a very robust zero post-processing, mass-producible CMOS photonics platform. And I also worked on integrating photocurrent sensors into all the microrings. So this is a picture of the chip testing station and the CLO chip, which is now wire bonded instead of flip chip. That's a big deal for us academics because this is very fast and cheap, and doing high density kind of advanced packaging with copper pillars and stuff has always been a challenge in terms of lead time and cost. So being able to wire bond CLO chips is like a total game changer. And here's the system that we have on there. It's got a fully isolated set of digital circuits for controlling the heaters in the microrings, and analog circuits for reading out all the photocurrents in the microrings. And here's an example of a zoom in of one of those systems. So there's an array of heater DACs on the north side, which is the same design as the previous heater DAC, except one fun comment about that is that we taped out in CLO before they had standard cells. Like they had version 0.5 transistors. And so I designed all the logic gates by hand, did all the timing by hand. And I think the area could be improved by about a factor of 2 if you used regular standard cells, which is like, how good GF is at really optimizing the layout of the standard cells compared to me. And then on the bottom, we have a high sensitivity capacitive transimpedance amplifier array that's very similar to what you would see in like a camera image sensor, but with like a little bit higher area than what you'd normally be able to fit into a camera pixel. And then we have shielded grading couplers. So there's germanium photodetectors in this process. And we basically put like a circle of germanium around the grading coupler and tilted it 90 degrees to try and reduce the crosstalk, because this time we do have a substrate. Unlike in 45 RF, where we didn't have a substrate, so that entire scattering and crosstalk mechanism was eliminated. So here's a picture of pictorially what the system looks like, with the digital circuits on the left and the analog circuits on the right, having basically a CMOS image sensor architecture. One important thing, just in terms of like time management, I was originally going to design an A to D converter on the chip, but like in order to hit the tape out deadline, I just realized, it's a CMOS image sensor. The analog interface is already serialized. We have address multiplexing and like shared analog buses and stuff. So just put a differential pad driver or pseudo differential pad driver and do an off-chip A to D, and that worked really well. That was actually able to get the tape out done on time. And if I try and done, like a 16-bit or 10, 12-bit ADC on chip, this whole thing probably wouldn't have worked. So sometimes you have to make those trade-offs in order to get things working in real life, even though it would be cooler if the system had all of that in the first revision. And there's a control FPGA that's kind of architecting the control of the system. Okay, so now I'm going to talk about how I added photocurrent sensors to all of the filter microrings in order to enable the improved version of the alignment. So the device on the picture on the right is kind of a device called an adiabatic ring with doped P and N contacts on opposite sides. And what that allows you to do is sweep out all of the carriers from the microring. So when you only have a single layer of silicon, like in 45 RF SOI, there's no rib waveguide, there's only one thickness of silicon. This is kind of the only way that you're going to get carrier sweep out in devices that are serially coupled. So they need 2 ring bus couplers per device, or a ring bus coupler and a ring-ring coupler. So that's kind of the origin story of this device. Then by the time I was ready to tape it out, we were in CLO. So I taped it out in CLO. But it turns out there's actually advantages to using adiabatic rings. So you need a pretty high voltage to extract all the carriers. But that's fine because the circuits don't see that voltage, just reverse bias across a photodiode. But the resonance wavelength variation is reduced in adiabatic rings. So if you kind of know roughly where to target the resonances, you'll need less tuning to get them aligned. So we just stuck with it. But there's, now that we have rib waveguides, there's, many different ways of extracting carriers. And so the picture on the left is an example of a 4th order filter that's built using these devices. So we get 4 photocurrents from this filter, and we have 4 separate heaters that we can use for alignment. And basically, when we fabricate these filters, we get the response that's shown, in the solid lines. It's actually not too misaligned, owing to the lower fabrication variations. Like the alignment of the filters initially came out way better with these devices than the uniform rings in 45 RF, but we'd like to align it fully and really get like very low passband insertion losses. So that's what we're trying to do. And here's just a picture of the capacitive TIA. So basically, there's an integration capacitor that we're taking photocurrent, which is on the order of nanoamps from these microrings, because it's all parasitic absorption mechanisms. We're integrating on a capacitor, and then we have a whole bunch of circuits organized in order to allow that to be done, say, very, very nicely. And there's also correlated double sampling. So there's 2 sampling capacitors, and they're producing a pseudo differential output signal. And that allows you to eliminate some of the noise and offsets in the system. And there's a bunch of standard circuit tricks here, like the low leakage sampling switch, that are just deployed in CLO to build a really good low photocurrent sensitive transimpedance amplifier. So here's like an initial pass at doing the alignment using the on-chip photocurrent sensors. So the 4 photocurrent plots on the left are basically taking each of the rings and then aligning it to its maximum photocurrent point, which doesn't actually produce an aligned filter, interestingly enough, and then running an optimization at the end for the photocurrent in the last microring, which is proportional to the dropped power. And as you can see on the right, we get a pretty nice aligned filter when we do that. But again, the convergence of the algorithm is not great. This works maybe 80 or 90% of the time. What is really exciting about this system, though, is that we're basically taking delta sigma DACs that are driving like 4 milliamps into these heaters and switching at a gigahertz very aggressively. And we're operating that, within like hundreds of nanometers of a photocurrent sensor that's sensing like single-digit nanoamps. And because we've done a very careful job on the layout and the isolation of analog and digital, it turns out that the crosstalk is equivalent to only like picoamp scale photocurrents. And so we're able to successfully read out, like 10 nanoamps while driving a switching waveform of many milliamps. So that was not guaranteed. And it's really great that worked out. And that's another benefit of monolithic integration, is that the parasitics of all these interconnects are very low. So you can get away with kind of better circuit designs and circuit topologies, like switching drivers for the heaters, while not contaminating your sensitive TIAs. One comment I will make, though, is that our mitigations for the crosstalk didn't exactly work. We have about 75 dB. This is a test site where the gratings are like right next to each other, so it's only 40 dB. In the systems, it's like 70, 75 dB, so we'll have to use a little bit of off-chip filtering. And in the future, we can improve that by increasing the grating coupler spacing and then also trying flip chip packaging and substrate release, even though we don't technically need to. Okay, so like, what is the way that you take advantage of these photocurrent sensors? And the answer is to use a model-based calibration algorithm instead of black box optimization. And the way that works is we basically model the energy in the resonators using coupled node theory, which allows you to build a state space model of how this whole filter is working. We couple that to a thermal crosstalk model. So all of the filter resonance frequencies are temperature dependent now, and those temperatures are set by the heaters and the thermal crosstalk matrix. And we solve for all the photocurrents. So when you do that, you basically start with some known factors like the ring-to-ring and ring-to-bus couplings, which have relatively low variabilities, and intrinsic losses, which you can probably measure with loss rings or kind of ballpark to be roughly in some area, and it's good enough. And then you have some unknowns, which are the resonance frequencies and the thermal coupling matrix. So you're basically trying to engineer a set of measurements on your filter that will allow you to estimate all the unknown matrix elements. Then when you have a model, you just invert the thermal crosstalk matrix and put omega n wherever you want it to be, hopefully all aligned and at the same wavelength. Yeah.
So thermal coupling matrix, like process variation, or why did it know?
Well, it could be known, I guess, if you did some very detailed simulations and you knew exactly which boundary conditions to use everywhere. But in practice, it's very difficult. So I think it's unknown. I do think that like if you characterized it once for a particular system, you could probably reuse it and it wouldn't vary that much from chip to chip. Okay, so I'll just very briefly go through the calibration algorithm. So the first step is you sweep the first microring, you estimate its resonance. Then you sweep the other microrings to get the thermal crosstalk terms. And then you park the first microring at its maximum photocurrent on resonance. Then you sweep the second microring and you hold the first microring at its resonance using the estimated thermal crosstalk term. And that lets you get the second resonance for microring number 2. Then you park microrings number 1 and 2 on the resonance wavelengths. And then you basically go down the chain for as many microrings as you need to, now using the inverse of the estimated thermal crosstalk matrix in order to continue basically keeping all the microrings aligned. This assumes that the thermal crosstalk matrix is symmetric, which is not necessarily the case, but it's kind of good enough because once you get microrings 1 through 4 all roughly aligned, what you do is you basically take all the microrings and you sweep them simultaneously. And now you've got 4 data traces all at the same time of a roughly aligned filter. And you basically just run an optimization algorithm to take your unknown CMT model parameters and then tweak them slightly in order to fit the expected photocurrent to this actual photocurrent response. And then finally, once you've done that, you can basically snap the filter wherever you want it. So this plot is kind of showing on the left, the red curve is where a simulated microring filter started. And then if you look on the right curve or on the right plot, you'll need to do that in order to get the details of why this algorithm is necessary. So if you just do steps 1 through 4, just trying without, just trying to basically maximize photocurrents with a little bit of crosstalk cancellation, then you end up with a blue curve. So the filter is like kind of aligned, but its passband is not really in the right place and its shape is not really the right shape. So when you do the model optimization and then finally solve for the microrings being in exactly the right place, you get a perfect match of the filter to its intended design target. So, in principle, we have the ability to measure the photocurrents and align the filters, and the algorithm works in simulations. And so the next step is to put that on hardware. And I'm hoping some students volunteer to do those measurements and write a paper about that with me. And then finally, what's really nice about this thermal crosstalk stuff is that you can easily keep augmenting this thermal crosstalk matrix with like thermal crosstalks to more devices on the chip until you build up a matrix for the whole chip. And that way, when you only have like a quantum signal, like megahertz of photons going through the filters and basically no photocurrent, you can keep the filters aligned as you're tuning everything else. So that's kind of, why we think the model-based approach is necessary for future scalable systems.
Question.
Yeah.
So I guess one question I had was the gain didn't seem really like obvious from the plot. So I guess
okay, so if you do optimization, you don't even get here, right? All I'm saying is that you basically use the photocurrents to do steps 1 through 4, and you're like almost there, and then you get exactly there by doing the final model optimization step. Obviously, like if the only thing you care about is kind of roughly the passband insertion loss is pretty close to the design, like you don't have to do that, but it'll still work. But like in general, in integrated optical systems where you want like particular responses that are predictable from your filters, and like in particular when you care about the phase response, like if you care a lot about the group delay variation and stuff, you really want like your filter to match the intended design. Because, for example, if you're using this like in a serial link, right, like all your simulations can go straight in the trash can if your filter has like the wrong phase response and it doesn't have the right center wavelength, right? So like you kind of need your filters to go where you intended them if you're building a bigger system. And I think that's also true for quantum systems, because it turns out we do care about the phase that's imparted on these photons by the filters. We didn't get there in terms of like the theory side, but it does matter, like if your filters are imparting different phases on the photons.
Also, quick follow is so how much like granularity you needed for the thermal crosstalk matrix? So I guess like kind of like the granularity in the sense that like you can be as precise or as fine as possible, like running this circuit, and this, and this, and this, and like whatever goes on. Or like you can just like say like.
Well, I mean, it's like the thermal crosstalk decreases pretty quickly as you move across the chip, right? So like the thermal crosstalk within the filter is something you have to compensate. Thermal crosstalk from filter to filter is probably something you have to compensate, and with the source ring in the same system. From system to system, like it's not clear that you really need to worry too much about that, especially if your whole substrate is on a tech, right? Because the substrate is how you conduct the thermal crosstalk. And so if you have a very wide substrate between the 2 points and the whole thing is like anchored very nicely to like a thermal ground on the bottom, then you stop having to worry about thermal crosstalk beyond a certain point. But the silicon and the micro rings is like right next to each other, so definitely there. So I think like I would say per system, we probably need to do this, and then maybe system to system, each one has their own separate. And now I'll just talk a little bit more about the source ring in 45 SPCLO. So first thing that we did is improve the heater design, and now we have about 60% of an FSR tuning range instead of maybe less than 10%. So we're really getting there in terms of being able to just target these resonances wherever we want them. One more pass on this heater design and improving the voltage swing of the circuits, and we will definitely be able to tune an FSR. And another thing that's really exciting is that we have some prototype source rings in 45 SPCLO that ended up with very high intrinsic Q factors. So for a rib waveguide, we're getting Q factors on the order of 100K. And then for the L-shaped waveguide, we're getting Q factors on the order of like 300 or 400K. Although I think it could go higher if you just move the contacts further away. The rib waveguide just has really wide spacing to the contacts. We really didn't expect to be measuring these types of Qs, so we didn't really optimize for it. But the extrapolated losses are very low, like sub dB per centimeter and sub 2 dB per centimeter. And if we re-optimize the ring bus couplings, because again, they were designed for lower intrinsic Qs, we think we can hit over 1 gigahertz per milliwatt squared pair generation rate efficiency. And if you do the exact numbers, it's like 1,000 times higher than what we had in 45 SPCLO. So that means you can turn the pump power way down. If you have large numbers of sources on the chip, you don't need an exorbitant amount of pump power. And the Raman noise is going to go way down. On top of that, in CLO, the waveguide is thicker. So you're inherently going to have less Raman noise because you're confined more in the silicon. Silicon does have a Raman peak, but it's at a very particular wavelength offset. That's not where we get the signal and idler pairs. It's like the amorphous cladding materials where you got molecules all over the place in different orientations. You get this like broadband noise that's bad. Yeah, and then finally, I'll make a comment about heterogeneous versus monolithic integration. So there's some stuff you can't do with monolithic integration, like some annealing steps to get very low waveguide losses because it'll destroy the transistors. But we think there's a lot of value in doing monolithic stuff, especially for quickly developing the scale of these systems, because we're basically not dealing with any of the bottlenecks of packaging here. Like we have in the system that I showed, better density than 50 micron advanced packaging because we're able to serialize the analog and digital interfaces to the photonics. And on top of that, the whole chip is designed with a single tool flow. So there's no difficulty of synchronizing like a CMOS team and a PIC team and dealing with like how all the bumps are organized. And like if you do that for like 100 bumps, okay, maybe you can kind of do it semi-manual, it's okay. But when you try and scale that to thousands or tens of thousands of interconnections, it becomes like a whole work on its own to do that properly. And you only find out if you do it correctly once you put everything together. So being able to wire bond out is a huge advantage and lets us go way faster than if we were doing heterogeneous and at much lower costs that are practical for academic investigations. And then, once you really know what you're building, okay, maybe you do want to go heterogeneous and like do a version of 45 SPCLO that has like better waveguides and annealing and stuff like that in a separate electronic circuit. Okay, so that concludes the quantum stuff. I'm going to go a little bit over time and talk about enabling optical circuit switching in AI data centers with fast tuning channel drop filters as the final part of the talk. Okay, so totally switching gears here. Everyone kind of knows that interconnects are starting to become a bottleneck for scaling up data centers. Like, you even listen to like popular tech podcasts, and they're talking about like maintaining coherency between large numbers of GPUs and stuff like that. Like, that wasn't the case 5 years ago. So this is an example from 2020. Google had a presentation at Hot Chips where they were talking about machine learning scale out, and they're basically showing that like this layer where you're moving information all to all between all the different processing units is starting to consume more and more of the total execution time for training as you're scaling up the size of the model. And I'm sure by 4 years later, the problem is only becoming much worse. According to NVIDIA, there's a need for high bandwidth, low latency interconnects with topologies that match the communication patterns. So is optics going to come in and solve this by moving everything at the speed of light? So Google showed that they're able to build an optical circuit switch as a network switch in their data centers. And they've actually deployed that already. This is a paper from 2022. And here's a roadmap of how Google is doing the high-speed serial links using pluggable optical transceivers. But there are some issues with this approach. Basically, the way they're doing the optical circuit switch with like a free space MEMS mirror array inherently has a very large size. It has high cost. You can see this is a massive box with lots of free space optics that have to be aligned. And they're doing all kinds of tricks in order to compensate for the yield of those mirror arrays. And then it has relatively slow reconfiguration of 10 milliseconds. So if you're trying to send bursts of data that are pretty fast with low latency, this isn't suitable. And then on the right-hand side, the pluggable modules are based on coarse wavelength division multiplexing. So like either one or a few channels that are operating at very high data rates. And that inherently means that you have high size, high latency, and high power, because you're doing like pretty heavy error correction in order to get all those transceiver channels to operate at like many hundreds of gigabits per second each. And so basically, optical circuit switching is only applicable to the slow reconfiguration of higher layers in the network. I just really want to point out, like, a lot of people are selling, optical means everything is connected at the speed of light. But like an analogy you can think of is, let's say that instead of having BART run like one train every 15 minutes, right? And then people could go to work, you had BART run 2 trains per day, one gigantic train at 9 a.m. and one gigantic train at 5 p.m. Basically, what would happen is if you're a little bit late to the 5 p.m. train, you're kind of screwed. Like, you have to wait at the BART station until 9 a.m. the next day in order to get on the train and go back home. So like just increasing the width of the pipe by trying to put a ton of data onto one wavelength is not a great solution. Like, you actually have to care a lot about the latency of these things, and latency is like separate from raw data rate. Yeah. I don't know, but that's kind of different, right? Like, RF over fiber is just directly modulating like a millimeter wave signal, and that's not really used in data centers, so I'm not really an expert on that. Okay, so here's some enabling technologies that we in the group and at Berkeley think are going to be able to change this paradigm. The first is doing a high radix, low latency silicon photonics MEMS switch. So this is being developed in Ming Wu's group, and basically you can build very high radix switch with cheap silicon photonics technology that switches in sub-microsecond scale. And the second is microring-based silicon photonics dense wavelength division multiplexing links. And so this is actually becoming more and more popular in the industry since it was first developed here. Basically, what you do is you try and parallelize with a large number of low data rate links that are error-free. They don't need error correction or DSP or all this like power and area and latency consuming stuff. You can think of it kind of like a UCIe link over optical. And you can co-package these chiplets directly with the XPU with a UCIe link to it instead of running some kind of wire to an external pluggable module. So that helps you a lot. And actually, there's a number of companies now developing this. So IR Labs, obviously we know, but Light Matter has pivoted to this. There's a company, Renovis, that's doing this, and Escape Photonics just started on this. So and others. So it's really, people are kind of seeing the light on this stuff. Okay, so what's the problem? So let's say that you try and put together a whole bunch of these links, and each XPU gets its own DWDM transceiver, and they're connected together with a MEMS switch. The issue is that we're using thermal tuning in order to tune the microring wavelengths. And there's a little bit of wavelength variation between all the lasers in the system. Like, it's prohibitively expensive to finely tune the wavelengths of every single laser across the data center so that they're precisely matched, and you don't have to reconfigure the link when you do the switching action. So even though you can switch pretty quickly, it still takes on the order of milliseconds to lock to the new set of wavelengths with the tens of microseconds reconfiguration, or tens of microseconds thermal time constants of thermal tuning. So we kind of need a faster way of doing this. And so here's something that we came up with as another use for that adiabatic ring, which is basically to, instead of use it in reverse bias and extract carriers for the filters, we use it in forward bias. And the reason for doing that, for doing channel drop filters, is that forward bias has very high electro-optic shift per volt. So it's compatible with deep submicron CMOS drive. But conventionally, it burns a lot of power, and the self-heating of the forward bias modulator actually limits its shift range. So on the left is kind of conventional version with a rib waveguide. You put contacts on both sides, and you inject carriers in perpendicular to the direction that light is propagating inside of the device. Whereas in the adiabatic ring, what you do is you put the contacts on opposite sides of the ring, or you could segment it however you like. You don't have to use an adiabatic ring. You could have an L-shaped ring and more segmentation depending on the bandwidth you need, as I'll show in a second. And basically, in order to get the same amount of carrier density, just doing rough ballpark math, you need about 60 times more current in the rib waveguide. And that's where that power consumption is coming from. So like in the adiabatic ring, we're basically reusing the same carriers by keeping them inside the ring for longer, because now their transit time is much longer. And we can have a more energy efficient shift while still having high electro-optic coefficient and much, much less self-heating. So you can actually get more range. Now, the funny part about this is that, like, if you tell this to people, basically everyone says it's not going to work, because the intrinsic region being long should introduce a lot of resistance, and that should basically like kill your current. But it turns out not to be the case, because actually the PN contacts are really good at injecting carriers, and those resistance effects come in at, like, when you actually do the math and the simulations, they come in at a much higher current level than you might expect. So in order to demonstrate that, just kind of in general and not relying on a particular device measurement, my undergrad Ilham set up a nice simulation framework where we basically compare parallel carrier injection with varying lengths of waveguide with perpendicular carrier injection using a conventional rib waveguide. Both of these are simulated in 3D FDTD and numerical charge. 3D FDTD is used for the rib waveguide, even though it has translational symmetry, so you could have done a 2D simulation. Just because I want to be absolutely sure that the simulation setups are comparable for the two, there's no bug in the scaling or anything like that. So just know that they're both simulated in exactly the same way. And I'll just like quickly guide you through the key points of the simulation study results, which are also submitted to CLIO this year. So the first one is that we're looking across a range of CMOS swings that's like 1.8 volts. So it's compatible with the transistors in the process. That's kind of the range we're limiting ourselves to. The second is on the bottom left, which is that if you take a look at the phase shift efficiency in terms of pi per centimeter, so segmenting a 1 centimeter waveguide with varying subsegments of parallel injection versus the whole thing perpendicular injection, you can see a massive power benefit to doing the parallel injection, which actually persists for much longer than you would expect. It persists across the entire CMOS swing here. So you can see there's a little bit less benefit due to the IR drop in that intrinsic region all the way at the top end of these curves, but there's still a very large benefit. And then the third thing on the bottom right is that the way that we're getting that shift efficiency, like I explained, is we're basically trading it for transit time. So the step response of these parallel carrier injection filters is much slower, roughly proportionately to how much we're gaining in terms of energy efficiency, because it turns out the forward bias voltage that you need in order to inject the carriers is not increasing by that much. And another nice thing in the bottom middle plot is that you can see that all of these things transverse kind of the same fundamental phase shift versus propagation loss curves, because you're just injecting carriers. So it doesn't matter which way you do it. And that's like a really good consistency check on the simulations. Okay, so we taped out 2 generations of devices that do this. The first one is a 10 micron radius microring in C-band, and the second is a 5 micron radius microring in O-band with some improvements to try and make it work better in forward bias, because the first ring was just designed for reverse bias. And I'll just go through the highlights of the measured performance for the C-band filter, which are in Clio 2022. The first is that we get about 200 gigahertz of shift before we get the turnaround from self-heating. And that's enough to navigate multiple channels of like a DWDM link. The second is that we still have an intrinsic Q on the order of several thousand across the useful shift range. And okay, this is not hundreds of thousands, but for channel dropping filters that need to support like tens of gigabits per second lengths, you actually want to couple them pretty strongly with large line widths. So this is totally acceptable. The third is that we're burning only hundreds of microwatts of power to do this versus tens of milliwatts for the thermal phase shifter that was on that chip. And the fourth is that we're 100 times faster than non-undercut thermal phase shifting. Now I'll go through the performance of the newer design in O-band. So it's 5 microns radius, which is going to mean that it should have higher voltage shift efficiency. And we've also doped the entire contact heavily P and heavily N and widened them with the anticipation that we're not going to need as high intrinsic Q factors. And we really want to increase the slope of that forward bias IV curve. So the previous device had light dopings and long narrow contacts for high reverse bias voltage that you need for carrier extraction, like 10 plus volts. And this one is just designed for forward bias. So again, we have intrinsic Qs of several thousand throughout the shift range. And we also, so this was submitted to FIO this year, and Ilham presented it. So, really impressive that he got a conference paper together as an undergrad. But since then, we've done the transient measurements and a comparison to like a heavily optimized thermal tuned microring that you might otherwise use as a channel drop filter. And the key highlights are that the forward bias microring is 1,000 times faster. So it's still way too slow for data modulation. But if you can lock 1,000 times faster, that means that instead of milliseconds, you're now taking like microseconds to do the locking, if you don't improve anything else about the way people are normally doing locking. And so you can kind of get the latency way down. The second is that we have better shift per volt, so 350 gigahertz range in this device as expected from the improved contact design. But the power has gone up. So we actually have similar power consumption to a thermal phase shifter with 2 nanometers of shift. And we have more power coming into the device. So there's more self-heating. So that's the trade-off you make by segmenting this device differently and making it smaller with a shorter intrinsic length. So I think these results are like surprisingly good, and it's kind of fun that like basically everyone's intuition about what that intrinsic region would do has previously prevented anyone from trying it, and we just accidentally had one of these devices and like realized that, hey, this actually can work. Okay, and then what's really awesome is that this device turned out to be useful for Sunjin's project. So Sunjin is basically now taking this and using it to build an 8 lambda DWDM fast lock receiver that's going to integrate with the MEMS switch that Ming Wu's group is doing and the MEMS switch drivers that Eric is doing, and like kind of try and build a whole system demo. So it's like, this is all designed by Sunjin, and it's really awesome to see that the device was useful for building a large system. Okay, we're basically almost done. So I'm just going to summarize the work. The first is that we built an electronic photonics single photon source. That's the first time anyone's done that. We developed tunable high extinction pump filters and introduced a lot of new techniques for doing it better. And then finally, there was this like fun side project, which an undergrad helped out a lot with to make it really happen, which was building the fast tuning DWDM channel drop filters. And I really want to thank Vladimir for having an awesome group that like spans so many different topics where we were able to like, find a use really unexpectedly for one of these devices and put it into a big system. Okay, so what are the future directions that we see for the electronic photonic quantum technology platform? So we kind of started with quantum photonics and 45 nanometer CMOS, but we can also integrate the 3.5 pump lasers, which Foundry has also done, already done, but for datacom. We can also integrate waveguide SNSPDs and SPADs in order to bring the single photon detection into the same system. And when I first made this slide, it hadn't been published yet, but it turns out PsiQuantum has already done this with niobium nitride SNSPDs. So there's kind of like there's a proof of concept that you can really fabricate these in a totally CMOS compatible way. That's really exciting. And then we can add electro-optic materials in CMOS to build a high-speed, low-loss switch. So these are just two examples. One group like flip lithium niobate after doing a substrate etch, and the other is Lumiphase, which is basically adding barium titanate waveguides. PsiQuantum is doing something else where they have a silicon nitride waveguide and a thin layer of barium titanate everywhere. And that's necessary for doing the high-speed switching for a quantum computer. One thing I will mention that's cool is, so we're using thermal tuning in order to move all these microrings for the quantum system. And you could argue that like that's not going to work at cryogenic temperatures like that you need for SNSPDs. So this whole platform is bogus. And PsiQuantum actually recently showed that with the undercut, which we're also using in order to isolate the heaters from the substrate, they're able to put a functioning SNSPD and a thermal phase shifter within like a millimeter or two of each other. I don't think they have exact numbers, but they have them on the same chip. The whole thing works. And that's how they're doing a lot of their phase shifting. So they can operate those thermal tuners up to room temperature on the same chip where the SNSPDs are at 4K. So that's actually a very exciting and like non-obvious demonstration. And so eventually what we want to do is build a single chip, turnkey heralded single photon source for electronic photonic quantum systems on chip. Okay, great. So now I just want to go through the acknowledgements of all the people that I worked with. So obviously, first of all, thank you like hugely to Vladimir for accepting me into the research group and having this really awesome project. Like I knew when I was going to do a PhD that I wanted to kind of combine physics and electrical engineering. And I think that this is kind of the perfect type of project to do that with, and also some optics. So I think it was like, it was a really great time to join the group and work on this stuff. Thanks also to Milos, who is the lead PI on this whole electronic photonic integration project. So that was originally an NSF grant, and then we just continued to work after that. But the work originally started in Milos's group, and we kind of started, adding electronics to it, adding carrier extraction to it, building bigger systems around it, and really pushed, I think, pretty far what we were able to demonstrate in that platform. And then also thanks to Prem Kumar at Northwestern, whose group did all the quantum measurements for the SNSPDs. Prem is really like an awesome collaborator because first of all, his research group was like the first place where people observed four-wave mixing and not four-wave mixing, but quantum correlated photon pair generation in silicon waveguides. There were two research groups that were kind of tied for that around, I want to say 2007. And so I think it must be pretty exciting for Prem to see like where the technology ended up since then and kind of being involved in like really scaling that up and taking advantage of being able to do that in silicon. And then obviously I want to thank the PhD committee. So Alp and Dan. Dan taught me nonlinear optics and quantum optics. So that turned out to be very useful. And I want to thank Ali for being on the qual committee. And then I actually want to thank my MEng advisor, Rajiv. So I only came into Rajiv's group kind of by accident because I wasn't able to find an MEng project, and I asked him for advice, and then we found something in his group, and totally by like a series of coincidences and accidents, I got exposed to this electronic photonic integration work and learned about Vladimir's group, and then decided to come to Berkeley. So it's like it's like a series of lucky coincidences and accidents that I came here, and it all started with Rajiv. So thanks Rajiv for that. And then finally, thanks to the BWRC staff for basically making the research center like run really smoothly and being a nice place to work. I think that really helps kind of your mindset when, you know, you're in a place like this that feels pretty serious and nice and well put together. And then finally, I want to thank collaborators and students. So on the photonics side, a bunch of students from Milosh's group designed or helped design the photonic devices. That's Imber, Joseph, Georgie. And then thanks to Ilam, my undergrad, for designing a bunch of photonic devices and doing like a whole tape out as an undergrad in CLO and setting up the flow to do that with GDS Factory and Calibre Data Prep. And then thanks to Sydney, Panos, Christos, Boji, and Pavan for being really close collaborators on the electronics that were designed here. In particular, I want to thank Sydney because like the first 2 years of my PhD, I was basically like incessantly, you know, bothering Sydney for help on like, how do I do this on the infrastructure? Like, it's not working for me. Can you help me with this? It was just like nonstop barrage on Slack. And he took it really well and actually helped me do a lot of stuff. And without him, you know, I wouldn't have been able to get very far in those first couple of years. So, you know, he contributed so much that he's kind of like on all the papers about this stuff because it wouldn't have happened without him. And I hope I've been able to pay it back, you know, somewhat for the future generation with Ilam and other students. And then thanks to Anirudh Ramesh in Prem's group, who did all the quantum measurements. So anything with an SNSPD, he was behind the wheel, basically aligning those things and taking the quantum measurements. Then finally, I want to thank companies. So IR Labs and Global Foundries kind of sponsored all the tape outs here. And without them and like a steady supply of like one or two tape outs per year, we wouldn't have been able to get very much done at all. So that's like, you know, we were really lucky to be kind of in this era where IR Labs is taping out like all the time, and we constantly get chip area through Vladimir negotiating it for us. So that was a real enabling factor. And finally, I want to thank Astronis, Keysight, and Project Tara at Google X for welcoming me in various roles to do work there during my PhD. All right, so with that, I can take any questions.
Thanks everyone for sticking around. I don't know if you have anyone on Zoom, maybe quickly a Zoom, give them a chance to ask a question. There's still a few people. Okay. But there's still congratulations. Okay, everybody see? Okay. If no Zoom questions, any quick questions here? Okay. Okay. Yeah. I mean,
For the forward bias tuning devices, did you guys include the surface absorption rate when carriers?
Oh, that's a good question. Yes. So in the simulations that I showed, those do not include surface absorption. However, we then reran a set of simulations just looking at the IV curve with surface absorption, and it dropped by something like 10%. So yes, surface absorption matters, and it very slightly decreases things, but it is also not the killer that you think it might be. Yeah, and that's actually, so we used 100 centimeters per second, I think. There's like, you know, maybe some debate to be had on exactly what value to use there. But we also have device measurements, and at some point we're gonna try and close those two against each other. One big difficulty we had though is that numerical, so you need to do a thermal charge co-simulation in order to actually get that turnaround point and the full efficiency. Numerical charge only allows you to make your contacts, like your metal contacts, thermal boundary conditions. So they just take all the heat out of your device. So the simulation time blows up and you get the same result anyway. So we kind of need to move this over to Centaurus at some point if we want to get really serious about optimizing the devices.
okay. Any other questions?
Just have one basic
Huh?
question.
Yeah.
So, what determines the resonance frequency of the signal and wavelength? You explained it in the beginning.
Okay, so in a microring, every time you have an integer number of wavelengths in the medium line up inside the microring, you get a resonance. You do millimeter wave microrings, you know this, right?
Yeah.
You know all that stuff. So there's a free spectral range because there's like an infinitely, you know, many number of resonances. And so what happens is that the adjacent resonances like +1, -1, +2, -2, +3, -3, those all have energy and momentum conservation for signal and idler pairs being generated. And so you get quantum correlated pairs generated in every single frequency band. So you pick one resonance, you pump it, they go all over the place. Now, the dispersion engineering in the microring is only done for like the +1, -1. So that's where most of them go. And then we only filter those out. And so we're just looking at those, but they're generated at equal offsets in every direction.
Once you design your ring, you know the resonance frequency of it.
Pretty much, like you know the FSR to a very good degree. You don't know the center frequency to such a good degree, which is why you need the thermal tuning. Adiabatic rings really help with that a lot. Like, you know, to an extent that kind of surprised me too. So maybe at some point we'll investigate non-uniform rings for doing the actual four-wave mixing. It's a lot harder to optimize them because they don't have the circular symmetry. So you can't just run a 2D mode simulation for the optimization. It's you know, it's a lot more computationally intense.
Okay, any other questions? People are good. Okay, thank you, Danny. All right. Everyone, okay.
There's also record-breaking of so.
Yeah. Sure.
So I'm applying for some faculty.